Let's get started with domain 1 and talk about ingesting and storing data. And let's get started with some fundamentals and talk about the first two steps of the machine learning engineer lifecycle: collecting data and processing data. So after you collect and store your data, you can then begin to process that data. And this would be step 3 of the well-architected machine learning lifecycle, which is data processing. Let's pause here and go back a bit further for the needed fundamentals of this exam and talk about the steps for the data engineering lifecycle, which are generation, storage, ingestion, transformation, and serving data. So let's quickly cover the first two steps of the data engineering lifecycle before we talk about collecting and processing data in AWS, which is the focus for this task statement of domain 1. The first step is generation, which is where the data originates from. So it is your source system. And remember earlier in the fundamentals lesson, I said that the first step of the machine learning engineer lifecycle is to collect data. And sometimes the collection of data is the responsibility of domain experts, but as machine learning engineers, you can also participate in this step. Your source system might be an IoT device, a transactional database, an application message queue, and so on. And for the generation stage, the data engineer or the machine learning engineer consumes the data from a source system, but does not necessarily control that source system. The next stage of the data engineering lifecycle is storage, which is a focus for this task statement from domain 1 and part of the first two steps of the machine learning engineer lifecycle. So for this exam, ensure you can choose an appropriate data store to store the source data, and also ensure you understand different use cases and different AWS storage services to ingest your data from the source system into AWS. And also remember about data lifecycle storage policies, and ensure you understand how to extract that data and ingest and process that data into your machine learning algorithm to train your model. And a few questions to ask yourself are: which AWS storage service is best for your use case? What format is the data in? What are the access patterns? Is the data streaming? And does the data need to be merged from multiple sources? And other questions too. So for the exam, ensure you understand how to use the AWS streaming data sources to ingest data, such as Amazon Kinesis, Apache Flink, and Apache Kafka. Let's move on and talk about choosing the right data type for your workload. There are many different types of data sets, and you need to understand how to transform different pieces of data before using that data to train the model. Choosing the right format is a key step in the performance optimization of your analytic workloads. And for the exam, ensure you understand that AWS also supports the processing of your data with AWS services such as Amazon RDS, Amazon S3, AWS Glue, Amazon Comprehend, and more. And ensure you know which services can work with and store structured, semi-structured, and unstructured data. And ensure you know how to model structured, semi-structured, and unstructured data in AWS to choose the appropriate storage and processing options to get valuable insights from different data types. So for structured data, we have Amazon RDS, Amazon Aurora, and Amazon Redshift. For semi-structured data, you can use Amazon DynamoDB, Amazon DocumentDB, Amazon Athena, and S3. And for unstructured data, you can use S3, Amazon Recognition, Amazon Transcribe, and Amazon Comprehend. Let's pause again and go back to the fundamentals needed for this exam. Machine learning engineers need to have a solid understanding of different data structures and algorithms to design and implement efficient and scalable data processing systems. By using the right data structures and algorithms, machine learning engineers can optimize performance, improve scalability, and reduce processing time. So let's pause for a few definitions. Data structures represent the data relationships and refer to the way that data is organized and stored in a computer's memory. They provide methods of sorting and accessing data effectively. Some data structures are relational databases, NoSQL databases, data warehouses, distributed file systems, message queues, tree data, and hash tables. And algorithms are a set of instructions or rules that computer software, web pages, programs, and hardware use to complete a task. Each provides a way to access data, but also to respond to a command in order to complete a task. However, if an algorithm is designed for a specific data structure, using it with a different data structure will lead to inefficiencies in your results. For example, you might need to implement a sorting algorithm to sort a large data set. You can work on unstructured, semi-structured, and structured data formats such as CSV and JSON, or columnar formats such as Apache Parquet and Apache ORC, with your data stored in Amazon S3 by using Amazon Athena, which lends itself to querying data as it is without the need for data preparation or an ELT process. And using columnar data formats can help you with your schema evolution. Also, you can use AWS Glue for automated ETL jobs to transform data from one schema to another, and you can help manage schema changes during data movement and transformation processes. You should also consider compression when choosing data formats, because efficient compression can help queries run faster and reduce costs. It can also lead to reductions in the amount of data stored in a storage layer, alongside improved network and input-output throughputs. Using splittable formats is also an option. These formats allow individual files to be broken up so they can be processed in parallel by multiple workers. Similarly to compression, this can also lead to reductions in query times. Often you need to choose between compression or splittable formats because applying both is currently not well supported for analytic workloads. And that might be dated because, I am constantly learning, things in this field are constantly changing. So please let me know if that's no longer the case. So for data ingestion, a machine learning engineer might use AWS Lambda to write code that handles data ingestion tasks. For instance, they could create a Lambda function that listens to an event source, such as an S3 bucket. The function is initiated when new data is uploaded to that bucket and performs actions like parsing, transforming, and loading the data into a data warehouse or database. For data processing, you might use Amazon EMR and AWS Glue to write code using programming language like Python or Scala to define data processing jobs using these services. You can use frameworks such as Apache Spark to distribute and parallelize data processing tasks across a cluster of EC2 instances. And for real-time data processing, you can use Amazon Kinesis and write code to consume and process streaming data. And you could use AWS SDKs and Kinesis client libraries to interact with the data streams. For data transformation and to perform complex transformations, you can use AWS Glue and write code using AWS Glue's Python-based ETL framework to define transformation logic, such as data cleansing, aggregation, normalization, and schema evolution. For data storage, you can use Amazon RDS or Amazon Redshift for structured data and write SQL queries to interact with that data. For semi-structured or unstructured data, you can use Amazon S3 and the AWS SDKs to read, write, and manipulate data that is stored in S3. In AWS Glue, the join transform gives you the ability to combine two data sets into one. You specify the key names in the schema of each data set to compare. The output dynamic frame contains rows where keys meet the join condition. The rows in each data set that meet the join condition are combined into a single row in the output dynamic frame that contains all the columns found in either data set. And in Amazon Redshift, you can add the new data to an existing table by using the merge command. For workflow orchestration, you can use AWS step functions to build serverless workflows by defining state machines. Then using programming concepts, you can define the workflow structure, conditions, and actions. Now, this might be a great place to pause the video. That was domain 1 and task statement 1.1. We're going to move on to task statement 1.2, and we're going to talk about transforming data and performing feature engineering. So machine learning is so large, and there are so many different types of data and problems to solve, and you will not do the same practices for every solution you're working on. So for this task statement, I want to talk about preparing your data for training and steps to take before training. In earlier lessons, we have mentioned transforming and processing data to then use that data to train your models with the different algorithms. We also talked about different data types, different types of data sets, and how we need to transform different pieces of data before using that data to train our model. So let's define a few different types of data. Useless data is data that does not have statistical relevance to the problem being solved. So it has a high cardinality, which means that the data has no correlation to the label you're looking for. For example, if you need data to help make a diagnosis that someone might develop diabetes, then indexes, IDs, account numbers, names, and email addresses would be useless data. Binary data is data that has two possible values, for example, a yes or no, or a 1 or 0. Continuous data is data that is measured on a continuous, quantified scale, also called interval data. For example, if you're tracking weather temperatures, it is represented by a number and continues to grow as the day continues on. Also, another example is if you're tracking your age and height or age and weight, the data continues as you age and grow. Categorical data is where data gets more interesting. There is categorical ordinal data, which is the order of the data matters, but the distance between the values is not quantified. For example, if you're collecting ratings of a dive shop, and if that dive shop is recommended by others, you might find categories of likely to recommend or unlikely to recommend. There is also categorical nominal data where the order is irrelevant. An example might be if you're tracking the color of hair. So unlike categorical ordinal data, the order doesn't matter. If you have green eyes and brown hair, and you have brown eyes and brown hair, the features of your eye color do not matter, and the order of that data does not matter. It's just the fact that is found by looking at unique value counts. So let's dive deeper, because it is important to be able to know the difference between the two types of categorical data for the exam and for the real world. If you're collecting data for recommendations of the dive shop that we just mentioned, on the x-axis, you would have the category likely to unlikely, and on the y-axis, we have a value. Let's use a linear relationship to say that someone is unlikely to recommend the dive shop would have a value of 1. But what if that changed to a likelihood to recommend the dive shop with a value of 5? The relationship between the value and the category makes sense because a value of 1 is not likely and is not great as the likelihood and the value of 5. And if we have a neutral rating, that would have a value of 3. But you can say that a rating of 5 is 2 units better than a rating of 3. And it makes sense to quantify the relationship between the numbers and the ratings. So customer satisfaction would be categorical ordinal data because we do not know the distance between likely and unlikely, but we know that they are in the correct order. If we did not know the distance between the data points, then it would be continuous data. Now let's talk about categorical nominal example. So let's say that I'm interested in the preference of scuba diving t-shirts to try to predict the colors to make and increase my scuba diving t-shirt sales. Well, we would still have our value on the y-axis still, but the category we might have more specific things such as colors, such as pink, orange, blue, and green. So if a blue t-shirt has a value of 2, does that make the pink t-shirt with a value of 3 better than the blue t-shirt? Does it make sense to quantify the relationship between pink and blue like this? Because in this example, a pink t-shirt is not 1 unit better than a blue t-shirt, and it doesn't make sense to quantify this relationship between the colors, and it doesn't fit on this graph. So this would be a categorical nominal example because the order is irrelevant. Text data is a word, sentence, or document. Words can be categorical data that might need to be encoded in a certain way, so be careful there. But if it is a sentence or document, then it is easier to categorize that as text data. An example is sentiment analysis. Temporal data is date, time, and order. It is a time order that events happen in. An example is a log file. For example, the temporal data might track a sensor and the time a pool heater was turned on and off. And I don't know about y'all, but I hate swimming in cold water. So temporal data has a flow that might be considered before you pass the data into the machine learning process. Let's also talk about feature encoding. So far, we have downloaded our data and analyzed the data to see what kind of data we have by looking at the different features. But before we pass it along to a machine learning algorithm, we could take steps to optimize the data to make it more efficient for the algorithm. There are 4 types of encoding methods for continuous, ordinal, and nominal data. And those encoding methods are binning, normalizing, mapping, and one-hot encoding. Continuous data binning creates bins of different ranges. So if we're tracking people's ages for our diabetes-related data set, we might have bins for people in their 20s, 30s, and 40s. And then people are placed in the bins by their age. And let's say that there are huge bins of people in their 50s. So it is condensed, but it also provides more meaningful information because we take the continuous data and make it categorical. Continuous data normalization is a type of encoding that needs to relate the data in ranges so that the machine learning algorithm can understand the values. In our data, and at this point, the algorithm does not know that we have data for age and data for temperatures, but it might add a preference to some of the numbers. But you can use a formula to normalize the data and put the ages and temperatures on the same scale. And then the algorithm can use regression to use the data within some kind of range, and by normalizing the data, we have not added any preference on the data, and prevents the algorithm from being influenced by higher values. Categorical ordinal data mapping can encode satisfaction rates. So you could add a range of numbers to the satisfaction range or ranges. And remember, we saw this earlier when we were talking about if people would likely or unlikely to recommend scuba syndrome as an excellent dive shop. And to encode this data, you define your satisfaction rates and then map the satisfaction to the satisfaction rate. Nominal data mapping does not have a relationship between values. It is just facts. It uses a unique count, and then you can add a column for each unique value. Then for each record, you look at the value in the table. So if your color is pink, it has a value of 1, and that is not better or worse than another. And this value doesn't make sense. Instead, the algorithm can identify the unique counts in the data set. For example, we have 3 colors, blue, orange, and pink. So we have a unique count of 3. So the algorithm will add 3 more columns to the data set. And then for each variable, we look at the value in the table. So for the color pink, we add a 1 to that column and zeros to the other columns. And now the data has been encoded that the record is pink, but it has removed the relationship between the colors. And then all of the other records are also encoded. And this is called one-hot encoding. One-hot encoding is the process of creating variables, and this technique is used for categorical values where the order does not matter. One hot encoding technique is used when the features are nominal, do not have an order, and for every categorical feature, a new variable is created. We've talked about different types of data, and specifically text data. So let's move on to talk about natural language processing. That is the area of machine learning that looks over text and documents. There are different algorithms you can use with NLP, natural language processing, but pre-processing and processing the data is important because if you have a document that is full of text, how do you make sense of that data? So let's talk about pre-processing text data before you pass it into the machine learning algorithm. Let's say that you have a quote written by Ocean Ramsey. We are not greater than other animals, but we should take the responsibility to look out for them. Show compassion, show a kind form of coexistence, lend a hand to conservation efforts. How does machine learning make sense of this quote? Well, you can tokenize the quote and take every word out and give it its own token value. So the first words are sorted, and you will see that some of the words are repeated or similar. Then you can categorize the words together. Then you can add the words into a table, which is called a bag of words. So you can add the words, and then below you add how many times the word appears in the quote. Then you can look at the words and determine if the words help understand the meaning and reduce the weighting of the words that occur frequently and are common words that outweigh the words of meaning. And you can use the term frequency inference document And you can use the term frequency inverse document frequency to filter out words. There is also stop words removal that finds words such as they, a, and, but, what, and so on. They are all common words and do not usually add meaning to the sentences. So it removes those words and reduces the sentences and can lose meaning. But from a statistical point of view, it adds more information as to what the sentence is saying. There is also stemming, which can be applied to the quote to examine each word and examine the language stem of the word. For example, compassion is from the Latin word compate, which literally means to suffer with. But be careful because cannot can be changed to can, which does change the meaning. Let's talk about methods to deal with missing data. Algorithms need complete data sets, so we need strategies to deal with missing data. If we have a data set that is missing data, you can ask the domain expert if the missing data is somewhere else or if the missing data is zero and the system that produced the data interpreted the zero as nothing. Is there a reason the data is missing, and can they share the data? Or is it the problem with the collection of data? One option is to remove the rows of data that have missing data, but you need to make sure that you still have enough data to perform the training. If there is too much data missing to delete the rows with missing data, then you can remove the column or feature of that missing data. And if we go back just a little bit to having a little bit of missing data instead of deleting rows, you can also impute data into the table. You can take the strategy, for example, the mean value of the column and take the average and insert that number into the missing data. So let's say we do that and we end up with 311 divided by 7, which equals 44.43. And then we plug 44.43 into our missing data. But remember, this data might be okay, but it is not correct. So you have to look at the method used to impute the data. You can use regression to impute the mean and apply a linear regression to the data you do have, and then plot your missing data onto that line. The new data points are still wrong, but they might be more right than they were before. Let's also talk about how to deal with unbalanced data. First, ask the domain experts to look at your unbalanced data set. Is there more data that you can use? More data might help balance the data set. And second, you can also choose the right measure of success, which we'll talk about in an upcoming lesson, on performance metrics, on training models and the algorithms they're working on. Choosing the right measure of success helps because accuracy is not a useful metric sometimes for data sets. If your unbalanced data is mostly one data value and your machine learning algorithm determines the value that is most common is accurate, then that is not useful because the algorithm will be accurate for the most part. Sensitivity and specificity are better measures, and the F1 score that combines both is even better. And again, we'll cover these later on under testing and performance. And third, you can make the data using oversampling or synthesized data. An example of unbalanced data might be data on a rare disease, and because it's rare, there is not enough data. There's also fraud, which is unbalanced because most transactions are not fraud. Let's bring back our missing data chart and add in diabetic type. And we have all type 1s and only 2 type 2s. So this is unbalanced data, and we can undersample the data and randomly remove the overweight class of data and remove some of the type 1 diabetic data. Undersampling is randomly removing the overweight class of data, but this can also remove a lot of data and can cause issues. A better strategy might be oversampling our data so that we can count the type 2 diabetics 5 times and duplicate that data. Oversampling the data is to copy the underweight class and then count them more times, but this can persuade the algorithm to be too specific to look for unbalanced data, but again, this might not be the best strategy. You can also use synthesized data and create realistic new data. Synthesizing data helps to create realistic new data. It is made up data, so we have to be careful, and you should use the domain expert here to be extra cautious. Let's move on and continue talking about transforming data and performing feature engineering, and again start with the fundamentals and feature engineering, which is a very broad topic. So let's define what feature engineering is and how it depends on your data sets and the problem you're trying to solve. Feature engineering examines the data type and what that data means. So we can take features we already have in our data sets and put that data set through a process to generate new features, which can condense features down to a new feature. If all of it relates, it can help the machine learning algorithm do less while training the model. Let's say that you have a data set of sales for different scuba diving stores. You can feature engineer that data from the different stores into a total sales data set by adding together all of that data and creating a new feature called total sales. And then you can format that data, and now you have a new feature and a new column of total sales, and you can get rid of the other data. We have created a new feature from existing data that we had. For binning, we can bin our continuous data, which is a form of feature engineering. Remember from our previous examples of data with ages, we create age bins of 20s, 30s, 40s, and 50s. This is a form of feature engineering because we are creating new features from existing data. We also have temporal binning, where you can take a feature such as time and convert the time into the hour of day. And for feature engineering, there's also additional data sources. So let's say that we have dates that scuba syndrome is open. We can add in another data set of holidays that are recognized as official holidays in the United States. And these holiday days are often used for people to take vacations and visit family. So this adds a new feature to our data set, and you can combine these two data sets together to create a new data set. We are not removing data sets, but adding a feature to the data set. So why would I do this? Well, let's say that I want to track to see if there are more sales on holidays and more dive charters on holidays. I can use that information to choose which holidays to close the store and which holidays the store should remain open for business. Here's a question. What is an example of sparse class grouping? If you have a data set with different classes such as A, B, and C, you can graph those to see which classes have more and which have less and determine the distribution throughout the data. Then the machine learning algorithm needs to give the same importance to all classes, and you can group the sparse classes and replace it with a new class size that is similar to the larger class size. So we can group the class B and D together and replace that group with a group X. And there are pre-processing algorithms. For example, a feature reduction algorithm can process the data and split out different features. Principal component analysis, or PCA, looks at all features of the data and engineers new features which represent the same features but with less dimensions. And we'll talk about PCA throughout this course. Let's move on to task statement 1.3 and talk about how to ensure data integrity and prepare data for modeling. Remember from the fundamentals lessons, we said the first step of machine learning lifecycle is collecting a lot of data to input into your algorithm. After the data has been collected, machine learning engineers process the data to ensure the quality of the data is high, ensure there is no missing data, ensure there is no erroneous data, and manipulating the data to be as efficient as possible to load into the next two steps of the machine learning lifecycle. For this lesson, I want to pause and cover some more fundamentals for upcoming lessons. Understanding bias and variance, which have roots in statistics, is important for machine learning engineers. Bias and variance are used in supervised machine learning, in which an algorithm learns from training data or a sample data set of known qualities. The correct balance of bias and variance is important to building machine learning algorithms that create accurate results from their models. Bias is a systematic error that occurs in the machine learning model itself due to incorrect assumptions in the machine learning process. Technically, bias is defined as the error between average model prediction and the ground truth. It describes how well the model matches the training data set. A low bias model will closely match the training data set. A model with a higher bias would not match the data set, have a higher error rate, and be more generalized, and so on. Now let's define what variance is in machine learning. Variance refers to the changes in the model when using different portions of the training data set. It is the variability in the model prediction of how much the machine learning function can adjust depending on the given data set. Variance comes from a highly complex models with a large number of features. High variance is when you introduce new data points. It is unpredictable and varies a lot, and it's not a stable predictor of the new data that is added. A few characteristics of a high variance model are noise in the data set, overfitting, and more. A model with low variance means data is close to where the model predicted it would be. Models with a high bias have low variance, and low bias has high variance. Here's a question. What can you do if you need to take data that is taken at regular intervals? We looked at time series data in an earlier lesson, and time series data usually has observations that aren't taken at regular intervals. For example, a data set could have some observations that are recorded hourly and other observations that are recorded every 2 hours. If you're using a forecasting algorithm, it might require the observations to be taken at regular intervals. Resampling gives you the ability to establish regular intervals for your data set. And you can either upsample or downsample a time series data. Downsampling increases the interval between observations in the data set. For example, if you downsample observations that are taken every hour or every 2 hours, each observation in your data set is taken every 2 hours. The hourly observations are aggregated into a single value using an aggregation method such as the mean or median. Undersampling reduces the interval between observations in your data set. For example, if you upsample observations that are taken every 2 hours in an hourly observation, you can use an interpolation method to infer hourly observations from the ones that have been taken every 2 hours. And you can resample both numeric and non-numeric data and use the resample operation to resample your time series data. If you have multiple time series in your data set, you can use AWS services, features, and tools to help standardize the time interval for each time series. It is important to understand that we randomize data when appropriate before training that data. Also, we split the data into training data and test the data. But we also need to ensure that our data is formatted efficiently before loading into the algorithm to complete the training. Let's pause here again and ask another fundamental question. Why do we need to randomize our data? We've already mentioned this in earlier lessons, but when we're trying to teach the algorithm to recognize the differences between images, if we pass the data in groups and not randomized, then the algorithm will think everything looks like a fish, and the algorithm will be confident that everything is a fish. And if we're changing our weights and biases as we're processing through the images, the model will start to have weights and biases that are prejudiced towards the fact that everything looks like a fish, and trying to change the inside of the model becomes difficult. But if your data is randomized and you start to pass the images into the model, it will see the difference of all the class types that are in the data set. And each sample image going in will be randomized. And even though it is more difficult for the machine learning model to solve, it is the actual problem we need to solve. And it will adjust the weights and biases interactively as it goes through all of the class types. Let's pause here and go back to the very beginning where I stated when appropriate. So what is an example of when you should not randomize the data? What if you're looking for the relationships between the data? An example is if you have time series data set of records throughout the day starting at midnight to midnight the next day. So in this case, you might use a recurrent neural network to load in data points and make a prediction of possible times to turn off the pool heater based on what has happened in the past. So in this scenario, if you randomize the data, then you lose the context of that data. The ordering of the data is important, so you would not randomize the data in this case. Let's dive deeper now into why we split data into training data and testing data. Well, this is done because the model now has training data set that it can use to adjust the weights and biases. And this data directly affects the training of the model and the outcome of that model. And if you use the same data set to evaluate the performance or accuracy of the model, then that is unfair because it is data the model has seen before, and that data is the same data that has directly impacted the values and parameters of that model. So it is best practice when appropriate to take a smaller portion of the data set as that test data. And this is not used in the same way as training data to test the weights and biases. But it is used to evaluate how well the model is performing with data that it has not seen before. The data is similar and has been collected in the same way as the training data, so that does make it a valid test. And a common split is 80-20. Here's a question. How do you split your data with time series data sets? Well, the testing split needs to also be in time series. And for me, at my level of machine learning experience, I would definitely ask for help from a domain expert to recommend where that split should be. Another way to do this might be cross-validation, which we will be discussing in an upcoming lesson. What are other things you need to consider when splitting up your data? Well, remember our supervised learning with tables. Some machine libraries and frameworks expect data to be loaded in two parts. One part of the data is the features, which are often called X, and the labels are separate and called Y. So how do you randomize and train and test and split this data? You cannot randomize one portion of the data and not the other, and you also cannot randomize both differently because the relationship between the features and labels would be broken. There are tools that help you randomize the way There are tools that help randomize the data the same way. Inside of scikit-learn, there is a train test split that takes the two inputs, and we can choose the size of the test to carve off, and we can also ask it to randomize. Let's wrap up this lesson and talk about data formats. So the actual data format and the way you present the data to the algorithm will depend on the format that the algorithm is expecting in the framework that you are using. So if you're using scikit-learn, Keras, or others, you need to look at the algorithm you have chosen and it will explain how it needs to have the data formatted and loaded into it. If you're using Python code at a lower level, you can use NumPy arrays and load that data You can use NumPy arrays and load that in with your data into the algorithm. You will need to complete some pre-processing beforehand, such as normalization of the data or one-hot encoding on string data values. If you're using higher level implementation of algorithms, such as Amazon SageMaker, it does have pre-built algorithms that expect data in formats such as JSON documents or manifest files. There are also different models that you can provide data to an algorithm. For example, an image classifier with images saved separately, and the algorithms have access to that from an S3 bucket. For file mode, the algorithm will need to copy the images, for example, to an EBS drive, then iteratively process each of the files. This can take longer because of the extra copying and processing of each file. For pipe mode, you can have a record IO file format type that takes all of the images and will create one file with all of the images. This helps because the consuming algorithm can load a portion of the files and can do a range load from that location, and it gives the algorithm the ability to stream the data into the training process. This is much faster than file mode and loading individual files one at a time. You can also use data quality rules in AWS Glue Data Brew, which is a visual data preparation tool to provide and prepare data analytics and machine learning. Also, AWS Glue Data Quality gives you the ability to measure and monitor the quality of your data and provides a managed serverless experience. And AWS Glue Data Quality works with data quality definition language, which is a domain-specific language that you can use to define your data quality rules. And then one more thing, I want to make sure that you are comfortable and understand encryption and techniques to encrypt data in AWS for your exam. That's all for Domain 1. I should have a new lesson video covering Domain 2, which is machine learning model development, hopefully by the end of this week.